Now, to calculate the vacuum diagrams in momentum space, recall that the Green's functions, there are no Green's functions for the vacuum graphs because the definition of Green's function was taking derivatives with respect to J of W or Z, but W or Z do not have vacuum diagrams. At J equal to 0, W is 1. Vacuum diagrams appeared in W tilde. So W tilde or Z tilde, so they had the vacuum diagram. So we are basically going to calculate Z tilde. Yeah, Z tilde is a constant. Z tilde of 0 is a constant because there are no external points. These are just constant. Each one is a constant, and all we are doing is the same position space expression. We are just writing them down in terms of the momentum space expression. That's what we should do. So so what we are calculating is Z tilde 0. So this is calculation 5. Z tilde 0, which is given by this diagram plus this diagram and so on. We are calculating, let us calculate this one, and this one is given by we know already the mathematical expression for that from the position space Feynman rules. That's given by Ig integral dx, then Ig integral dy for the two vertices, and then there are three propagators from x to y. Then we just write the delta x minus y in terms of its momentum space expression. So Ig square integral dx dy. For each propagator, I introduce a momentum. dq3 over 2 pi to the power d. And then the phases in the propagator is iq1 dot x minus y plus iq2 dot x minus y plus iq3 dot x minus y. Then 1 over I, the momentum space expression for the propagator, 1 over I delta tilde q2, 1 over I delta tilde q3. Right? Then I do both the x and y integrals. Ig square integral dq1 over 2 pi to the power d, dq2 over 2 pi to the power d, dq3 over 2 pi to the power d. If you do the x integral, then it will be a delta function imposing q1 plus q2 plus q3 equal to 0. So that is 2 pi to the power d delta q1 plus q2 plus q3, and same as for the y integral, the same thing happens for the y integral, delta q1 plus q2 plus q3. And then 1 over I delta tilde q1, 1 over I delta tilde q2, 1 over I delta tilde q3. So 2 pi to the power d cancel, two factors of them, and then I just impose the momentum integral So let us integrate out Q3. So IG square. Let me write. Okay, so I'll do that later. So integral dq1 by 2 pi to the power d dq2 over 2 pi to the power d 2 pi to the power d of for Q3 cancels, then 2 pi to the power d delta. Q3 is minus Q1 minus Q2. So this one of the delta function, if you impose for Q3 integral, then Q3 will be set to minus Q1 minus Q2. When you set that value here, put that value here, then it will be 0. So this is delta 0. 1 over I delta tilde Q1, 1 over I delta tilde Q2, 1 over I delta tilde minus Q1 minus Q2, which is same as Q1 plus Q2, of course, because Q1, because delta tilde is even function of Q, right? So that's the result. What you get is if you reorganize the way I have been doing for the last few calculations, you write it this way, and then integral dq1 over 2 pi to the power d dq2 over 2 pi to the power d times 1 over I delta tilde Q1, 1 over I delta tilde Q2, 1 over I delta tilde Q1 plus Q2. So that's the result, and the diagram will be, so again, let me write. So this is this calculation, one particular diagram. And the entire result will be this diagram plus. So the same diagram, but you have to figure out the momentum integrals. So you see Q1 and Q2, there are two loops here. There are two loops, and therefore there are two momentum which are freely integrated over, which are free, which are not fixed. And so you could write as, see, this one is Q1 and the other is Q2. So this is Q1 and say this is Q2 and this is Q1 plus Q2, right? So then the momentum conservation is preserved here at these 2 points, because Q1 plus Q2 coming in and Q1 going this way, Q2 going this way. Again, here Q1 coming, Q1 and Q2 coming this way and going here. So again, the momentum, so there are other terms, and here the point to make is that momentum conservation at each vertex. That's the diagram in momentum space. So I think we have calculated many diagrams now, and we are in a position to write down the Feynman rules for the momentum space diagrams. So let me write down the Feynman rules. An endpoint Green's function in momentum space is given by sum of all possible topologically inequivalent graphs with n external legs labeled by P1 to Pn, right? That's what we've seen. And endpoint Green's function in momentum space is given by sum of all possible topologically inequivalent graphs with n external legs labeled by P1 to Pn. Then all these momenta, these are labeled by, okay, sorry, this is labeled by this, and these are all incoming or outgoing. In a given graph, all lines are labeled by external or internal momenta, maintaining momentum conservation at each vertex. In a given graph, all lines are labeled by external or internal momenta, maintaining momentum conservation at each vertex. For any loop, there exists a momentum called loop momentum that is not algebraically fixed by momentum conservation in terms of external momenta. So for any loop, there exists a momentum called loop momentum that is not algebraically fixed by momentum conservation in terms of external momentum. These loop momenta are integrated over. And given this type, so following such rules, you label the diagram in terms of external and internal momenta. After doing that, to get the mathematical expression for them, you write for each vertex a factor of I times G. Then for each line carrying momentum p, this is basically a propagator. This line is basically a propagator. You write 1 over I delta tilde p for each loop momentum p, you have an integral dp over 2 pi to the power d, and then multiply by an overall factor, which is 1 over s. The symmetry factor remains there, 2 pi to the power d delta p1 plus p2 plus pn. This is the overall momentum conservation. Okay, that's the Feynman rule. So next, what we should do is that so far we have used the definition of the momentum space Green's function in terms of Fourier transform of the position space Green's functions, and then from those exercises were done to understand how to write Feynman rules. Now, once I understand the Feynman rules, I should be able to directly draw the diagram, label it, and find the mathematical expression. So that's what that is the practical approach that one would follow, instead of going via the indirect method of taking the position space Green's function and taking the Fourier transformation of that, the way we have done the calculations so far. So that's what we are going to do for a few exercises of writing down, drawing the diagram, and then following these Feynman rules, writing down the corresponding mathematical expression.